day.
That must have been a great afternoon.
Yeah, yeah, definitely.
Very good. Okay, well, thank you so much for sharing it with us and good luck for
Thank
the
you.
remainder of your study.
Thank you.
Um, you're very welcome. So we've just had a quick change of order. And so Ninesh, who is listed as going last, is actually going to jump in next. You're ready to jump in and share your slides, Ninesh? Yes? Ninesh is from the Faculty of Engineering, and his thesis is entitled From Data to Diagnosis, Advancing Performance Measurement at Signalized Arterials. I think I got that right.
Yes. Thanks, Felicity, for that. Hi, everyone. I'm Narish. Currently, I'm a student at School of Civil Engineering. My supervisory team has Professor Ashish Bhaskar, Dr. Shubham Sharma, and Professor Alex Bass. And as Felicity said, the topic of my research is from data diagnosis, enhancing the performance capabilities. So, what is it about? It is about intersection operations. So, everyone might have traveled through a signalized intersection, and the objective of intersection is to move people safely and efficiently. The thing that I focus on is efficiency over safety. Now, what threatens the goal of efficiency is a variation in demand. The arterial intersections always have different demand, different in morning, afternoon, evening, at night. So to maintain them, what's the answer an engineer seek is that the current setting that I have given for an intersection, does it work well with the actual demand or not? Based on the demand, we can categorize intersection as undersaturated, where I have more capacity, but I have less demand. Saturated, where the capacity is at demand, and oversaturated, where demand exceeds capacity. To solve this, to get answer to these questions, there are a lot of performance measures reported in the literature. I'll be focusing on the few aspects. I'll be focusing on the timing issues, coordination issues, and the highlighted performance measure. Now, what is the need for this? Traffic operations work on a very simple loop. We have data. Using that data, we get some quantitative performance measure, and those performance measure act as a trigger to know that something needs to be changed. But what do engineers need? They need to know if the intersection is performing poor, why is it performing poor? Next thing the engineer will need to know is where is it performing poor and at what scale? So the current literature gives us a good trigger that something is not performing well. But what we need is what can be changed after getting a trigger. So this thesis closes that simple gap from flagging a problem to knowing what might can be done about it. Now, to flag performance measure, there's a significant gap currently. The gap has a capacity to diagnose the issue rather than just triggering an issue. So that's the first issue. And the second thing that my thesis focus on is translating those performance measure which are at an intersection to a corridor level and a network level. So we expand the capability of performance measure from triggering to diagnosis, and diagnosis at intersection level, a corridor level, at a network level, increasing the spatial applicability of the current performance measures. So to categorize, I have identified two objectives that I'll be focusing on. First objective is to reformulate the current performance measure so that they can diagnose something, and second, apply those performance measure on a different spatial scale. To do that, I can categorize my entire thesis in three studies. Study 1 that will focus on intersection, study 2 which will focus on corridor, and study 3 which will focus on the network. The study 3 is directly related to objective 2, whereas the first two studies are for objective 1. Now, if I go ahead, sorry. Yep. The first study that will focus on the diagnosis of intersection. What am I focusing on? I'm focusing on a split failure, a flag without diagnosis. Now, what is a split failure? Think of it, you're driving on an intersection, you're waiting for a light to turn green, it turns green, you move ahead. But the green was so small that you were not able to clear that intersection. And that's what a split failure is. The green time provided is not enough for a vehicle to clear in one cycle. Now, how do we identify if there were vehicles that experience that phenomena? It is through loop detector data. So loop detector data are those sensors that you might see on an intersection. If a vehicle is on that intersection, the detector says that yes, someone is on intersection. We quantify how much amount of time a vehicle was on detector during green phase, which we quantify as green occupancy ratio, GOR. We also quantify how much time vehicle was there during the red phase, which we quantify as red occupancy ratio. But the issue over here is if I draw the occupancy and the number of vehicles clearing the intersection at a given time, the C region is where the phenomena is occurring. Region A is where there's a downstream blockage. The Q from the downstream is spilling back towards my intersection. And region B is the demand is less than capacity, but there's some Q spillback. So occupancy is getting elevated, but it's not getting as high as a split failure condition. So region C is the correct identification. Region A and region B are the misclassification of current method. So the current split failure method classify all of them as split failure, and that's a misclassification. We are triggering that yes, something is wrong, but we are not identifying if it's a downstream Q spillback or if the green given is quite less. So if I estimate the same values from the current method, the one that we see on the left, the red points are correct classification. The yellow ones and the pink ones are the wrong classification. So I just add one simple factor in the current equation. What that does is it moves the misclassification to the left of the threshold, hence eliminating the partial blockage cases. The yellow part is still the blockage case, and we haven't yet removed those misclassification. Now, to bring correct identification, what we propose here is we use another performance measure called as spatial oversaturation severity index. It is just the quantification of time where the vehicle was on a detector, yet it was not clearing the intersection, divided by the total green time, which is SOSI. So if you look at this figure, which I derived from real data collected from TMR's intersection, on the second row we have split failure, and on the third row we have SOSI or green utilization. Both of them indicate yes, it means that the system is triggering that there's a split failure, and it is also triggering that there's blockage, and that's what we see in the detector as well. Whereas in the second case, we see that there is split failure and there is no downstream blockage, and that's what we see in the data. So this bifurcates the two cases where split failure is due to less green, whereas split failure due to Q spilling back from the downstream blockage. And that helps us with my objective, which is using same performance measure, split failure, with another performance measure, SI or GU, to diagnose whether the issue is my current intersection or the issue is the downstream intersection. How this helps to an engineer is to identify where the change should be made. Should the change be made here, or should the change be made the downstream intersection? So that's my first study. Now, the second study is again bringing the performance measure from an intersection level to a corridor level and diagnosing something out of that. Now, what do we achieve in coordination? So you might have seen that whenever you travel along a long corridor on a straight direction, sometimes you see a wave of green and sometimes you not. The objective here is to get that green band. If you see a trajectory here, it's getting a consecutive green for two intersections, and that's what coordination is. Engineers usually achieve this coordination so that vehicles can flow without making a stop, increasing the efficiency of the corridor. But what goes wrong? These settings are based on assumptions of the speed limit, the demand, and many such things. This changes significantly on a signalized intersection. That's why we have a performance measure called percentage arrival on green, which quantifies how many vehicles arrived on green versus how many vehicles arrived on red. More vehicles arriving on red indicating that this coordination is poor. However, where this performance measure fails is that it quantifies all the vehicles stopping as arrival on red. If you see in the example I have given here, the dark trajectories are not arriving on red. They are stopping because the queue at the start of the green was so high that the vehicle had to stop before it could clear the intersection. So the engineer here is being told that vehicles are stopping. PAG tells us that yes, vehicles are stopping. The progression is poor, the coordination is poor. However, the engineer is not being told what should you change or where should you look so that the vehicles don't stop and they continue flow. So that's why what do? We break our green intersection or a green signal in three parts: a QCD, a coordinated band, and a post band. So if you look in the first region, before the vehicles arrive, the queue or the vehicles already at an intersection are flushed out, and all the new intersection or all the new vehicles coming from the upstream intersection flow without making a stop, which is a good coordination. Whereas in the second case, the queue length at the start of the green is more than the time we have given to flush it. That's why the new vehicles or the vehicle that should flow without making a stop join the back of the queue, make a brief stop, and clear the intersection. Now, using historical data, we can tell how many vehicles are or should be coordinated. Vehicles that should clear without making a stop. And based on quantifying a new parameter called overrun parameter, we can quantify which of the two intra-green zones, which is QCT or coordinate, should be updated so that vehicle do not make a stop and they clear the intersection. Now, first thing what we do is we identify the required coordinated band, how much should be the green region, or how should be the green duration so that it can serve the platoon or the vehicle arriving from the upstream intersection. We plot or we compare that with the actual settings and then we check if it's in line or not. The white region you see here means that the band given is in line with the demand, whereas the black region shows that there is some deviation from what should be the ideal design. And that's the first diagnosis we provide, that your design is incorrect, go and make some changes on your design. Now, second, the overrun parameter quantifies what was the relative clearance time compared to its intended clearing time. So if we look on the shaded region, these are the vehicles that cleared before or when they should. Whereas the right hand side, the dark histogram shows us that these are the vehicles that took more time than they should have cleared the intersection. So the first figure tells the coordination is good. The second figure tells us the coordination is bad. We get this for the vehicles that should be served in QCT, which is the queue clearance time, and we get the clearance time for the coordinated vehicles. Based on how much delay or how significantly further it is from its intended clearing time, we can identify which one is the suboptimal intrazone. Are the QCT vehicle taking more time to clear the intersection, or are the coordinated vehicle taking more time to clear the intersection? So this provides us a complete framework. If an engineer can assess progression, it can assess if the signal is wrong, and if the signal design is incorrect, what is the issue? Is my QCT incorrect or is my coordinated band incorrect? So that's the complete diagnosis we provide in our study 2, completing our objective of diagnosis at a bigger spatial level, telling an engineer what should be done and not what or there's some issue. Bringing to my third study, which is now again expanded on a network level. What we do here is we identify bottlenecks. Currently in literature, what is a bottleneck? So let's say Brisbane city, right? In morning, the Brisbane city is entirely congested. We cannot find an undersaturated condition. Now, it is possible that the settings of one intersection is so bad that the queue from that intersection propagates to the entire network, dragging the performance of entire network down. So it is important to identify such intersection. What this will tell an engineer, it will give him a strategic hold on what investment should be made. So based on identifying the bottlenecks, engineer can prioritize on that intersection, improve the performance of that intersection, improving the performance of entire network with the help of just one intersection. Now, how that's done currently in the literature is, if let's say we have a tree here, A, B, and D, if congestion is observed at intersection B, and after time T dash, there's some congestion observed at A and D, what they'll do is they'll just correlate them. However, it is possible that the two independent events are correlated. There's no guaranteed of, or there's no evidence-based identification of Q propagation. It's just a statistical correlation between two intersections using historical data. We improve that, and furthermore, there's another limitation here as well. Let's say for at one intersection, the Q is propagated from two different sources. So there are two bottlenecks in one intersection. Current method would not be able to bifurcate those two bottlenecks. One of the examples that I've shown here is this case. If you see at this intersection, the Q is propagated from the yellow intersection, which is just below that, and the Q is also getting propagated from the root 1 intersection. Current method will just consider entire thing as one Q. However, there are two Qs present here. So the engineer is shown a bottleneck based on statistical correlation and not from any proof or not from evidence. And that's where we bring evidence-based bottleneck identification. How do we do that? So if I relate back to my first study, which used split failure with spatial oversaturation severity index, which quantifies the amount of time intersection was blocked without moving a vehicle at an intersection. We use these SOSI values over a network of intersection. For example, the root intersection here is B. Now from B, because I have detector information, I can see that there is some SOSI observed at intersection D. And from intersection B, there's some SOSI observed at intersection A. This means that Q from intersection B is being propagated to D and B to A based on the detector information. We are not correlating them, but we have hard evidence of occupancy in this method. To showcase this applicability, this is a congested network of
Wrap
Brisbane.
it up now, Nanesh, just so you know.
Yeah. So we have two bottleneck here, bottleneck 1, bottleneck 2, and we can identify two different queues propagating over a network, and we're able to identify two separate queues. Finally, the conclusion, three studies, one diagnostic lens, study 1, diagnosis at intersection, study 2, diagnosis at corridor, study 3, diagnosis on over a network. And that's my thesis, from data to diagnosis, increasing the performance measures capability from trigger to diagnosis. Thank you.
Thank you so much, Nanesh. Sorry I had to cut you off briefly there, but yeah, we're just running a little bit over time. Just because we're just a little bit past time, we might just move on to our next presenter. But if anybody's got questions for Nanesh, I would encourage you can either put them in the chat for him or get in contact with him after this. It's an extraordinary amount of work you've done there, Nanesh, so well done.
Thank you.
Liam.
Hi, my camera's still working great.
Liam's from my faculty, from the Faculty of Business and Law, and Liam's thesis is on the longitudinal effects of live stream gifted subscription